So where we left off last time in photo management was at the end of this stuff about memory, different RAM subtypes. So before I go forward, are there any lingering questions about memory types, that sort of thing, that anyone would like to have resolved? Anything where you'd like me to explain more? Yeah.
I just want to know, how in depth should we know the differences between the different types of RAM?
Well, you don't need to know how they're engineered. You need to know their different performance characteristics. Does that make sense? Yeah. All right. So like regular RAM, know it's fast, faster than obsolete dynamic RAM, way faster than disk, used for running applications because that random access feature is important. Static RAM, know that it's super fast, but only when used in tiny amounts, right? You can't just put in a big brick of RAM in your static RAM in your system and have it work as or better than regular synchronous RAM. All right, so stuff like that. Obviously, you don't need to know how it's engineered because this is IDS 200. This is not computer engineering, what, 428 or something. Okay. Excuse me. Okay, so then we'll go ahead, we'll talk about RAID. So RAID stands for Redundant Arrays of Independent or Inexpensive Disks. Basically what it means is you, what? Okay. Basically it means that you have a bunch of actual separate disks within one single application housing. So RAID is still used even after the shift from hard disks to solid state drives. RAID still is out there. It's still a thing. And it's actually really important as an introduction to the concept of the cloud. Because just like you go to Facebook and all your data is stored somewhere out there, but you don't need to know the specific machines it's stored on. You just go to facebook.com and Facebook delivers everything to you. Same kind of thing with RAID. The user connects to the RAID device through the same interface, regardless of where their data is stored on the disk. You don't need to specify an individual disk where data is stored. Okay, you just say, well, I'm going to the disk drive. So from the outside user, it works the same. Now, there's a whole bunch of different RAID models that allow emphasizing different levels of write speed, right? The ability to change data that's stored quickly, or read speed, the ability to retrieve data quickly, or reliability, the improved likelihood that some kind of hardware defect won't ruin everything. So we'll talk about those in a second. There are three basic techniques: striping, mirroring, and parity. So I'm gonna draw for a second just to tell you what a RAID device is. Okay, so I have my standard disk drive picture. Oh, wait, I can't do that yet. I wish I could set transparent selection as a default because, right, I would save a lot of time doing that, let me tell you. Okay, so here's a disk. Sure, something like that. It's a little crooked, but you know what? It came out that way at the factory. That's not my fault. So there's another. There's another. All right. And all of these disks are combined in one RAID device. We'll drop that down to 16 for better. Okay. Whoop. That's the device. And it has an interface, what's called an I/O interface. I/O stands for input output. And the interface connects to all the different disks, right? And then some user connects to that. So here's some orange user on the outside. Okay? And so they can send data to and from the RAID device. Now, the three properties we're going to talk about. First one, mirroring, even though that's not the first one listed in the slides. Mirroring means storing multiple copies of data on separate disks. Okay? So for example, if you have a file that you want to save to your RAID device, if you have mirroring, it's going to save a copy to one disk and another copy to another disk, possibly a third copy to a third disk, and so on. Okay? So you can have different levels of mirroring too. You know, you have double or triple, whatever. Excuse me. Obviously, this will greatly improve reliability, right? Because if your file is stored on multiple disks, then if one disk breaks down, you still have the copy on the other disk, right? So that's good. Uh, read speed is unaffected by mirroring. Reason is, with mirroring, the system doesn't say, well, I'm going to, pull all three copies of the file. It's just going to randomly pick one, whatever disk isn't busy at that instant, say, oh, I'm going to pull the file from this disk and get it. So the read speed is the same, even though there's multiple copies there. Okay? But write speed is potentially slowed down. Reason is, every time you're saving the file, what happens? You are, in fact, saving three copies on three separate disks, right? Now, since it happens in parallel, if the disk drive isn't too busy, if the RAID device isn't too busy, it's still going to take the same time to copy one file to one disk. It's going to have three of those happening at the same time. If the disk drive isn't busy, nothing's going to get slowed down. But it does represent, 2 or 3 times as much work, right? If we're saving everything on 3 disks, that's 3 times as much work in the system to save a file. Meaning if the disk drive is busy, there's going to be a bigger backlog, okay? Because it's more work. Questions on any of that? Does that make sense? That's mirroring. Okay. Now, I should also point out that if you go looking at some of the links that are in the lectures, some of them can include numbers for the different RAID models, right? There are a bunch of different combinations of mirroring, striping, and parity implemented in different ways. And you can look up the numbers for those. You don't need the numbers for the exam. Just know what RAID devices are, know what mirroring and striping and parity are. So second thing, striping. Striping means breaking a file into segments and storing each segment on a separate disk. Striping worsens reliability if it's implemented just by itself. Reason is, suppose you have a file that you break into 3 segments and a segment gets stored on each one of those disks. What happens if any one of those disks breaks down now, right? Your whole file is irrecoverable. So that's a problem. So striping, it makes reliability worse. Read and write speed, however, are multiplied. And the reason is this network connection, this interface connection, that's basically a rounding error on how long it takes to get to your data, right? The big thing, especially in old-timey hard drives, is basically finding where the data is on each disk. That's the big delay. And because those 3 actions can happen in parallel, right? You can find the data on disk 1 at the same time as you're finding it on disk 2, at the same time you're finding it on disk 3. That's what makes the operations much, much faster, right? And again, you're pulling less data as well. So, you're pulling a shorter segment of data. It's all happening in parallel as well. So striping is going to make your read and write speed a lot faster. Okay? The cost of that is less reliability. Now, of course, you can combine striping and mirroring together, and you can kind of get the best of both worlds, all right? After allowing for the fact that, yeah, every option you do is in fact entailing more work, and then, saving a file still means you're going to have to save multiple copies of it. Also, mirroring is going to, burn through disk storage space faster too, obviously. So, you're going to need more hardware to store everything on. So there's potentially a cost issue there as well. Okay, mirroring, striping. Would anyone like to know more? All right. Well, the last thing to talk about is parity. And before I talk about parity, we're going to draw a picture, which will make sense in just a moment. Okay, so let's fill it. And we're going to give some sky. This is my standard day at the beach picture. Okay, and we're gonna fill that. We're gonna make a blue circle. We got some sun. That's nice. A very nice and oval-shaped sun there. Okay. Now, suppose your system has this initial copy and a second copy, right? It's made a backup somewhere. And suppose that over the course of days, weeks, months, years, something has happened and the image has been corrupted. Okay? And one of the two images, and it doesn't matter whether it's the original or the copy, right? Could be either, whatever. Oh, I can do this actually. I'm gonna flip it. Aha! See, I did that. I'm gonna flip it back. Okay, so whatever, one of the images got corrupted. Can an automated system that doesn't know what the original picture is absolutely supposed to look like, with two copies, can an automated system figure out which is the correct one? It cannot. That system, without some supplementary data of some kind, can't have any basis for saying, you know what, that should be orange. It could just as well be that it was originally orange and it turned yellow. The system isn't going to know. However, if you have a third copy is generally sufficient. Not only that, but with a third copy, you can tell not only which image went wrong, but you can tell where the error is, which is an important advantage over other techniques like checksums that we'll talk about, in a subsequent lecture. So for this, if the system has these three copies of the picture, it can look at them and say, it's mathematically possible that the sun started out orange in these two pictures and somehow ended up yellow. And that error happened at the same time in the same place on two separate files in different locations. It's mathematically possible that that kind of coincidence could happen. But it's vanishingly unlikely because first, corrupted data like that is actually a really rare event all by itself. And the idea that it would happen, twice in the exact same place in the same way is even more unlikely, right? If you know probability. So you can be very confident in that case that the sun should originally be yellow. Ta-da! And the system can recognize that. Now, parity checks are a way of providing that source of error detection and error identification. Okay, so I'm just going to get rid of that. I'm going to start writing about parity. Let's do dark blue. Okay. Without getting into the details about how parity checks happen, I mean, if you want, I have some links in the lecture slides. If you say, hey, I really want to know, by all means, go for it. But again, this is IDS 200, not, disk drive storage logic. So parity basically means there is effectively a third copy of any data that allows, the original data to be identified, and thus errors identified and corrected. Okay, that's what parity means in practice. Now, parity by itself, obviously it affects reliability, but in a different way from mirroring, right? It doesn't give a less probable likelihood that, some copy of the file will be unavailable. Obviously, if a disk breaks down, that's a different issue, right? What it does is if some tiny portion of the file gets corrupted, you can recognize what the problem is and fix it, right? So yeah, it does improve reliability, but in a different way from mirroring. Read speed, unaffected. Why? Because once again, there's multiple copies of the file there. The system's going to pick one at random, pull it, read it, ta-da, it's done, right? But write speed can potentially have severe impacts, all right? So imagine the case where you have combined parity and striping, and you want to change something. Well, the nature of parity means that you're doing it from a whole file perspective. So if you change one little bit on part of a file, you're going to have to change the entire file located on all disks to make sure the parity information checks out. Okay, so that's when combined with striping. So if your operations have a lot of small changes that have to be made, for example, you have a database stored on disk, and every now and then you're changing one record on the disk and updating it, and you're implementing parity with that, it's going to entail a lot of extra work. All right, so trust me on that one. So those are the things, basically what you need to know for the exam, what mirroring, striping, and parity are, and their practical performance impacts. Okay, and these become important because we're going to talk about Facebook and some of the problems they had as far as disks versus RAM and how they try to optimize their systems for speed at reading or writing. And just be aware in the back of your head that there are different ways to implement this. Okay, that there are different ways that you can achieve that. All right. So next, hard drive speed. So if you've ever cracked open a hard drive and looked at it, or if you've seen pictures of it, whatever, basically it's like a little record player. There's a disk cylinder that spins around just like a record, and there's a drive head that's like the needle for a record player that goes to the correct spot and starts reading or writing the data. Okay, and thing about old-timey hard drives, solid-state drives are a lot faster than old-timey hard drives were. Reason is, hard drives were physical, not electrical, right? They had to actually physically relocate the drive head and move it, just like the needle on a record, which typically took several milliseconds to happen. So anytime you did a different operation on a hard drive, you'd incur that delay, which is called a seek delay, where the drive head is trying to find the right spot to go to. It's seeking out the correct position, okay? RAM, of course, doesn't experience seek delays like that. It's just you pull data from anywhere in any random order. It's going to be very close to the same time as if you pulled it all sequentially. But it's more about electron distance than anything else. It's not really about being sequential. So for all practical purposes, RAM speed is identical regardless of whether the data is random or sequential. All right. I just don't want some junior lawyer telling me, hey, I looked this up and there's some special oddball cases where, it actually does matter a tiny, tiny fraction of a nanosecond where the memory, I was like, yeah, okay, but that, okay. Now, hard drives, solid state drives, whatever, they have a lot more memory per dollar as RAM. Okay, so I did a price check last semester, and a mid-range quality terabyte disk drive was about 50 bucks. I don't know, maybe it's down to like 40 bucks now. You can find cheaper ones, you can find more expensive ones, but ballpark number 50 bucks. Likewise, 8 gigs of probably DDR4 RAM, maybe DDR5, was 40 bucks back then. So comparable price, but about 100 times more expensive for RAM, because 8 gigs times 100 is 0.8 terabytes. Now, of course, if you're talking about DDR6, which is cutting edge, that's going to be more expensive, way more expensive than DDR4. Anyway, so hard drives, you get a lot more storage capacity per dollar than you do with RAM. But hard drives, even solid state ones, are much, much slower than the equivalent amount of synchronous dynamic RAM. In fact, for a lot of things, it's just going to be too slow, right? So I have a discussion of, how much faster is memory RAM compared to solid state drives? I don't know, around the order of 20, 30 times faster for a lot of cases. I mean, you can read the article and if you want, but just bear in mind, RAM is a lot faster, and we can leave it at that. The other thing, if your entire system was running on disks instead of RAM, you'd also need a lot more hardware. It would be a lot more work to optimize stuff because you can't change the contents of disks too many times. If you want to allow simultaneous access, like if there's a popular video that, suppose it's 2009 and Rihanna has just released some video that everybody wants to watch on Facebook, basically you'd need a whole lot of disks just to make sure that everybody could grab the file without waiting for the next person, prior person to be done downloading the file. So if it's a case where there might be 1 million people wanting simultaneous access, you're going to need a lot of disk drives on hand just to deal with that possibility. Anyway, and even so, response time would be slower, right? Because it would happen at disk drive speed, not RAM speed. All right. So as a solution to that, one of the things we talked about before was that businesses say, you know what, data that needs to be dealt with quickly, we'll put that in RAM. Data that doesn't need to be dealt with quickly, we'll put that on disk, right? And how much RAM you need versus how much disk you need really depends on the situation. So for example, suppose you're some business that has a very small cluster of data that's being actively looked at, right? So you're some business that sends out invoices and almost nobody ever looks at invoices like that are more than a month old. So you say, you know what, we're going to store this stack of last month's invoice data in RAM, and that's going to basically solve all our problems, right? Everything else going back as far back as the business has, we'll keep that on disk. We don't need much RAM. Facebook, on the other hand, even old pictures on Facebook are fairly often looked at, surprisingly often looked at. And so Facebook had a problem where even if they tried to store just the popular data in RAM, it was still going to be too expensive. They had to come up with a better, more sophisticated way of doing it. But basically what they're trying to do is balance cost and speed. And one industry example of this was Oracle's in-memory database cache. All right, so I'm gonna draw a little picture, and it's just a general picture of how this works for like any operation, really. So over here, we have a big brick of RAM. Okay, terabytes and terabytes of RAM. We don't really care how much. And over here, we're going to have a whole bunch of disks, right? Big tier of disks for permanent storage. All right. Now, when requests come in, ideally, we've stored the data that people are likely to want in RAM. So the requests can be responded to very, very quickly. Okay? That's the ideal. But we know that's not always going to happen, right? We know sometimes people are going to ask for some oddball stuff. And what happens then? Well, in that case, the request gets forwarded to the disks. And so I'll say here, forwarded requests not fulfilled by RAM. Okay? And the disks will have it because everything is actually stored on disk. Even the stuff that's in RAM is stored on disk because it needs to be permanent. So if there's some power failure there, you don't just lose everything, right? So everything is stored on disk, whether it's in RAM or not. Now, if that happens, right, that a request is fulfilled by disks, we'll say here, response fulfilled disk system. Okay? And then the response goes out. Now, the other thing you're periodically going to see in this kind of system is churn, right? So I'm going to mention this in just a second. We know that today's popular news is yesterday's forgotten news, right? Meaning the stuff that's in RAM today is eventually going to be just stored in disk tomorrow, right? At some point, it's going to be old news. It won't be something that people ask for a lot. Likewise, on occasion, data necromancy happens where things come back from the dead and are for some reason popular again. For example, you know, in that Captain Marvel movie a few years ago, there were a lot of songs in the 90s. I feel like my wife was personally targeted for that one. You know, or again, Thor Love and Thunder, I think had 3 Guns N' Roses tracks in the soundtrack. And I was like, huh, I guess I am the target, you know, age demographic, whatever. So that was all the stuff when I was in high school. So anyway, that kind of churn is going to happen, right? Where something that was old suddenly becomes, oh yeah, let's go watch that song. This is a great song. We'll see the video on YouTube, right? Stuff that hasn't been looked at much for a while suddenly gets looked at again. Okay. All right, this makes sense. All right, now the criteria for what goes here and what goes here, what goes just here, is basically popularity. So we'll talk, oh, and again, we say here backups may be synchronous or asynchronous. You can do them all at the same time, or you can do them like in batches at the end of the day, whatever. But, you know, just recognize that all the data has to be stored in disk for permanence. All right. Now, the in-memory grid is that same kind of thing I just did, right? Oracle's Time 10 system is one of those kind of grid system. So in-memory grids use the same RAM as your computer, but there's a lot more of it. And that means that for popular requests, the system can operate at RAM speeds instead of disk drive speeds, right? Which is potentially thousands of times faster than a disk-based system, especially in 2009 when Facebook was just using hard drives. Solid-state drives weren't really a thing then. Backup is also important. Volatile memory like RAM gets erased when the power is lost, right? Which is a huge reliability concern. You don't want somebody spilling a coffee into your system and wrecking everything. Okay. Next thing, caching, right? So remember, popular data, however we define popular, is cached, kept where it's easy to store, right? So caching is that simple principle. The stuff that you use a lot, you want to put where it's easy to reach. So for example, suppose you have some tools in your garage, right? Suppose you're like a tool guy and you got, power drills and a table saw, all kinds of crap. And those things are there, but you don't use them very often. Those are just for special projects, right? What you need every day is stuff like, wrenches, screwdrivers, hammer, pliers, basic stuff like that. So in your garage, right by the door, you put a little tool bag with all the stuff that you're likely to need, right? And then when you got to grab a tool, you just reach in, grab the bag, boom, you're done, right? It makes a lot more sense to store the tool bag right by the door than to, put a drill press or a table saw right by the door, because you're probably just not going to use that often, okay? Same idea with caching. There's a variety of ways where it can happen, but the first thing to talk about is what data gets cached. And the two terms that are used for that are hot and cold. So hot data rather, is data that's in some sense popular. And I'm going to say you can't really have data be popular if it hasn't been recently accessed, right? If it hasn't been recently accessed, then at best, it's data that used to be popular or might be popular again one day. So the minimum qualification for something to be considered hot data is that it has been looked at recently, right? Because if it hasn't been looked at recently, there's no way it can have been looked at often in recent history. Okay, the other one is cold data. Cold data is data that is used infrequently or hasn't been looked at recently. So, for example, suppose you went on vacation 10 years ago and you posted a bunch of very nice photos of that vacation on Facebook, and all your friends looked at them, and that was great. And for a little while, they were very popular. Okay? 10 years later, for some unknown reason, you decide to go back and look at one of those pictures. Now, I'm going to say that one view in 10 years is probably not going to automatically elevate that data to being popular again. Okay, now you could have different rules set up in your system that say, yeah, anything that's been looked at in the last 24 hours, we're definitely going to cache in RAM. Yeah, they might do that, right? But that's really a policy question. That's not really a definition of what's hot and cold. So, if it hasn't been looked at recently, it definitely can't be hot. If it has been looked at recently, it's kind of a system design judgment call over how recently, and it has to have been looked at to be considered hot, right? But cold data definitely, has not been very popular lately, okay? And like I said, that oddball case of sitting in storage for 10 years, one person looks at one thing of it, is that enough to elevate it to hot data? Probably not. But again, the system designers might make a different choice, right? So don't get too hung up on the details. Hot data is data that's looked at often or recently. Cold data, not looked at very often, not looked at very recently. Okay? All right. Now, there's different ways that caching can happen. One thing, for example, suppose your organization has a bunch of different servers, and some of them are newer and faster than others. Well, the applications that are more popular, more used by more users, you might want to put those on the faster servers, right? So that people are happier about all that. They get to what they need to do faster. Likewise, if you have database tables, right? Basically think of it as documents of data, and some of them are popular and some aren't. In order to reach them faster with physical hard drives, you could put the popular tables right at the start of a disk drive track, right? That way, as soon as the drive head moves there, it's in position to read that popular table. Likewise, if you're making lists of what tables are stored on what disks, you can put the most popular tables at the start of that list. So less scanning and reading is required to find them, right? So there's a lot of different techniques you can use to prioritize what's popular and what's not and get better system performance for it. All right. Now, replication. Okay, so replication is a basic question. What do businesses do, like Facebook do, when they have to keep multiple copies of the data, and where they keep it? Do they keep it all in one spot, in one system, in one physical location, or do they scatter it around the world, at one of dozens or several of dozens of data centers? So things that happen if all your data gets stored in one massive centralized location. Number one, it's going to be slower for a lot of users to get to. There's always inherent distance delays around the order of 1 millisecond per 100 miles. And so even though cables are a lot more higher capacity than they used to be, they don't actually push through the electrons much faster than they used to. Okay, so that speed delay is always going to be a thing. And if you're sending some tiny little bit of data, that's going to be about the same time. So, what?
Nothing.
Okay. It's a little jarring to me when I hear stuff. If you got to talk to people, you can write notes. All right. Anyway, I'm not going to come around to say, I saw you writing a note. I'm going to read it and, I'm going to say Susie has a crush on Bob. I don't care. Bob's a jerk. All right. Anyway, I apologize if anybody's named Bob or Susie. Anyway, those distance delays, 1 millisecond per 100 miles, are a thing. For example, if anybody plays Fortnite, one of the things you can do is look at, a different data center you want to connect to, right? So here, if you're probably playing on North America East. If you're in California, probably North America West. And they're going to have different ping times, right? If you play in like one of the Europe ones or Middle East ones, they're going to have different ping times too, probably worse because they're on the other side of the world. All right. Other problems that can happen, traffic spikes affect all users. So if there's a big rush in traffic, that's going to kind of ruin everybody's day, or other things like a denial of service attack, same thing. This third point, optimizing availability for all users is less effective. Well, one of the things that you want to do with caching is keep the popular data easily available, right? But think about it. If you're a data center just near Chicago, the things that people are interested in Chicago at noon are likely to be pretty similar to the things they're interested in at midnight, right? There'll be less people, and yeah, there'll be some variance of interest, but a lot of it's going to be the same local interest Chicago stuff. However, if you have a global coverage data center, that means the people who are keeping it busy at noon in Chicago are mostly going to be asleep when the people on the other side, like say in Australia, are looking at stuff in your data center, and their interests are going to be very different. And so in order to provide caching effectively, you have to really do a lot of churn throughout the day saying, oh, this stuff used to be popular in Chicago, but the Australia people are coming on. Let's recycle that, right? And the more coverage you have around the world, you're going to have that continuous flow of different priorities over time, and you're going to have to be churning your data in and out of your cache a whole bunch. Last, potentially brittle reaction to failures, right? If there's a fire, an earthquake, some lunatic with, a shopping bag full of C4 tries to blow up your operation, whatever, that's going to kind of wreck your whole day, right? It's a lot harder to coordinate that sort of thing, or a lot less likely to have multiple natural disasters hit different data centers at the same time. Okay. So the solution is decentralization, right? Decentralization means you have multiple copies of the data stored at separate server groups, separate data centers worldwide, right? And when necessary, those requests that don't have access to the local data can forward the request to other data centers that do and get it. So, for example, suppose I'm on vacation in Japan and I take a picture of something and I upload it to Facebook. It's probably going into the Japan data center at that moment, right? But what's going to happen is that there's going to be other people who I know from the United States. They're going to, at some point, log into Facebook. It's going to pop up in their feed that, oh, Doug just did this. And, they're going to pull that picture from Japan's data center. And pretty quickly, there's going to be enough traction on that probably. It might only take like 5 or 10 or 20 looks to pull that data center from Japan, pull that image from Japan and bring it to Chicago's data center. All right. So Initially, things probably get posted to near wherever they're posted, but they can drift over time if they become popular somewhere. General advantages of decentralization. Number one, less latency. Most users get their data faster. Number two, locally important data, like in the Chicago versus Australia thing at noon and midnight, can be cached continuously. So if your data center basically covers Chicagoland, boom, you put the Chicago data there. And for your data center on the other side of the world, you put other side of the world data there. If there is a system failure, it's only going to affect the local system. It's not going to wreck everything. And last, smaller database size. If your data centers are handling smaller batches of data, there's a lot of operations that are just going to be easier. We talked early on about scalability issues, things like veracity of data. It's a lot faster to do that, if your databases are smaller in one place. So, all right. Now, as far as Facebook replication, one of the neat things about Facebook is they take advantage of the fact that friendships and activity tend to be strongly correlated with geographic proximity. Basically, you're more active with friends that you are, near to. Right now, when you're in college, is actually probably the window where that might be some of the least true, right? Because you just got out of high school, you probably still have friends at high school back home, wherever that may be. Not everybody here is obviously from Chicago. A lot of you probably went to school and other people went to other colleges. So, your social network kind of, boom, instantly got dispersed in that window. But eventually, you'll get old and you'll tend to be more active with friends you're near because you'll say, hey, you want to get together? Let's go out, see a movie, get some food, whatever. And you're going to ask that question to people that you're physically proximate to, right? You're not going to call up somebody from the other side of the world and say, hey, want to go see a movie Saturday? Right? So most of the activity is with people that you're nearby. You have old friends who are distant, but it's just not the same. Anyway, so at each of those database locations, Facebook, this fact kind of helps Facebook build in the rules of what should be cached and what shouldn't be, right? It tends to happen that where you post something tends to be a pretty good location for where your friends are going to want to be able to access it. So that just kind of makes Facebook's life easier. Okay, the last bit here, we're going to talk about Haystack. So Haystack is the system that Facebook did to deal with a significant problem they had in 2009. Now, the x-axis here is age in days. So if you look real close or you have great eyes, you can see it's 200, 400, 600, and so on. All those intervals are 200s. So 1 year is about here, all right? The y-axis is cumulative percentage of accesses. That basically means what percentage of accesses are for photos that are so old, right? So you can look here, it starts to become visibly divergent around 40%. So, we could be charitable and say something like, okay, maybe something like 40% of Facebook views are for images that are posted like within a few days. But by the time you get to a year, you're still just barely over 80%, right? A whole 20% of the images Facebook is looking at, Facebook users are looking at, are more than a year old. And this problem fundamentally means if Facebook wants to get reasonably good performance for a very high percentage of photo requests, it needs to have a whole lot of RAM to do that, right? Because disk drives are slow, and these numbers say, you know what? You can't forget about these older pictures. Even ones that are like 3 years old, they're still like something like 5% of photo requests are for photos that are like years old. And the problem is just going to get worse over time, right? Because Facebook is going to keep on having a longer and longer history with occasional dips back into looking at older photos. So when I said, you want to keep in RAM what you can, but you can't build your whole system in RAM because exabytes of RAM is going to be way too expensive, this is the problem that Facebook was dealing with. So their situation also, Facebook was relying on very expensive content delivery services. This is kind of in the early days of Facebook. They didn't have all this infrastructure built in for themselves. So they said, you know what? Yeah, we're going to store people's photos on disks, and that's fine for the ones that are, very rarely requested. But for the popular ones, we're going to go through a content delivery service so they can deliver them quickly. But as Facebook got big, it started becoming prohibitively expensive to do that. first of all, there were more photos per user. Many were from years ago. Users still occasionally looking at the old photos. And to deliver all those photos fast enough, caching them in RAM, right, building that huge RAM system for Facebook would have been too expensive. Going through content delivery services, also too expensive. And worse, demand was still growing very, very quickly every year. So Facebook not only said, you know what, this isn't good now, it's just going to keep getting worse too. This is not a temporary problem. So if we very briefly recall our capacity equation from the other day, lambda, the arrival rate, is equal to S, the number of system processors, divided by T sub P, the time required for each process. Lambda is getting bigger. And to deal with lambda getting bigger, you can either add more system processors, but that's, right, dollars, dollars, dollars. Same thing as if you add faster ones, same kind of thing. Or you can reduce the time required to process the photos, the photo requests. Well, in fact, that's what they did. That was the magic of Haystack. So we're going to talk about it for a second. Okay, so key insight, instead of storing all the data as just one block of data, so when Facebook has a photo, it has the image itself, but it has a bunch of also what's called metadata, data about the data, things like who posted the photo, when they posted it, how big it is, what the permission level on it is, stuff like that, okay? Now, compared to the photo, all that metadata is really compact. It doesn't cost that much to store that in RAM. So one of the things Facebook said, hey, rather than having to do a lookup for everything, because what Facebook used to have to do is first say, oh, somebody's asking for a photo. We got to find where the photo is. And then we got to look at who posted the photo. And then we got to look at the list of people who have permission to see that photo, right? So there were multiple lookup operations involved anytime you pulled a photo for some purpose like that. But if you put the metadata in RAM, you automatically have all that information there. And the only thing you really need to worry about is where the photo is and actually pulling that. So in effect, what they did, well, we're talking, so I'll go to the next slide. In essence, the magic of Haystack meant they needed fewer disk input-output operations to retrieve photos. Basically, they didn't have to incur that repeated disk seek time over and over and over for a single photo request. The way they did it, right, again, put that photo metadata in RAM, not looking up the lists that were stored on disks, and they also had some supplementary techniques, like trying to store photos together in large files. So one of the things Facebook found is that people who, look at one photo of a series, there's a good chance they're going to look at all of them. And if all those photos are scattered around different parts of a hard drive or on different drives, it's going to take a lot longer to pull them all separately because of the seek time delay. But if they're all stored sequentially, you only incur that seek delay once and you can pull the whole string of photos. So Facebook put in a policy to encourage users to upload and download photos as albums. So the consequences for this, number one, system is a lot faster, right? Especially for that long tail of older photos, all the ones that are like a year, 2 years old that people are once in a while looking at. Sequential albums can be retrieved from disk much faster than the same set of photos stored individually and separately on disks. And the net consequence, without even adding any substantial new hardware, just this new way of arranging the data, Facebook's Haystack system basically tripled the capacity of the system overnight because they didn't have to incur that terrible seek time over and over. And by not incurring that seek time, by tripling capacity, number one, they didn't have to rely nearly as much on content delivery services, right? Their existing services were usually fast enough. And number two, they bought themselves a lot of time for growth, because before that, before their real amount of traffic was going to get to where it used to be before Haystack. Okay, cool. Well, that's all I got. One last thing. If you would like to read something about this Haystack, there's a nice article here. This is the one that I recommend, right? This first one in the bottom group. There's a little PDF. It is very readable as these things go. So if you want to learn a little bit about how they did it, you're interested, there it is. All right. All right, that's all I got for you. Have a good weekend. Don't come back